Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Khairil bin KAMARUDDIN.
And my name is Muhammad HAZIQ bin KHAIRIL AZRI.
My name is Muhammad Rizwan bin RAOF.
And my name is Ashraf bin SAFIEE.
So today we're gonna present about transmission line, no load and matching impedance for lab 4. So this is the result of the line length 150 km, and this is the value we got from lab 4. And as you can see here, there is not a bigger difference with the line length of 300 km, which is only increment of 1 volt compared to 150 km. So this is the schematic diagram. The connection begins from 3-phase power supply, and then goes to power quality meter, and then it goes through transmission line as we stated before, 150 km and so 300 km, and then goes to other power quality meter, and then the voltage drop will begin at resistor, capacitor, and also inductor.
Okay, so based on the data tabulated in table 1 and table 2, discuss the feature of the results based on the following arguments. Number 1, why the results of line voltage at sending and receiving end little bit different in case 150 km, which is the medium transmission line, but obviously different in the case of 300 km, which is the long transmission line. So the answer is, we can see from calculation and results, voltage drop is more in 300 km lines compared to 150. This is due to the fact that reactance is more in 300 km line. In general, inductance for whole conductor increases with increase in length. This makes high reactance makes voltage drop much more. This is a drop at the sending end and receiving end. So, with increase in length, voltage drop increases and receiving end voltage reduced. That happened in 300 km line, so that is why that much difference in that case, but not in 150 km line. So number 2, compare the measurement results with the calculated values, then make a summary based on comparative analysis. So the answer is from the first two tables. Number 1, voltage drop is more in second table, which is at 300 km line. And number 2, current is also more in 300 km line. And the third one, active power is 0, is 100 km and very less, equal to 1 watt. And the last one is reactive power requirement is higher in 300 km lines compared to 150 km line. So this is the table 3 result during line length of 150 km, and the table 4 shows the result during line length of 300 km. And table 5 shows the measurement values during matching, which is in line length of 150 km and supply voltage of 380 volts. And table 6 shows the measurement values during matching on line length of 300 km and supply voltage at 380 volt.
So the equation for power is U2 delta square over resistor, or R equals to U2 delta square over P. Is used to calculate the corresponding load resistance, which also represents the characteristic impedance. It said that U2 square is U2 delta is the line to line voltage across the load. So based on the calculation that we get, for a line length of 150 km, resistor equals to ZW, impedance W equals to 236.34 ohm. Then for the line length 300 km, R is equal to 237.09 ohm. Next. So this is the schematic diagram for the transmission line matching under load. The difference between the no load and under load is at the resistor. We can see the line, the resistor is connected. That is the load for this transmission line. Next. Based on the data tabulated in table 3 and table 4, we can suggest that the Ferranti effect observed in the long transmission line is more. At low loads, the receiving end voltage is higher. At higher loads, the drop in voltage at the receiving end is observed more in long transmission line. Voltage regulation is poor in long transmission line compared to medium. So this is also the base on the tabulated result in table 3 and table 4. When comparing the measurement result in medium transmission line and long transmission line, we get that the ohmic losses in the transmission is high in long transmission line, so the efficiency is less. As mentioned, the Ferranti effect is more dominant in long transmission line. And as load increases, the reactive power drawn by the line increases, which is the reactive power generated by the line. The rating of shunt capacitors and reactors to be used for long transmission line will be higher than medium transmission line. Long transmission line, the line inductance to be decreased by increasing GMD of the conductor. So the voltage drop in the line, the reactive power drawn by the line decreases at higher loads.
Okay, based on the data tabulated in table 5 and table 6, discuss the feature of the result based on following arguments. So the question is, now question 1 is, what is the relationship of those results in table 5 and 6 corresponding to the magnetic impedance issue? So the answer, we can see that long transmission line has a larger voltage drop than medium transmission line. It is because of the higher impedance in long transmission line. So question number 2 is compare the measurement results in medium transmission line and long transmission line. So the answer for question number 2 is the active power of the load for table 5 is higher than table 6. In table 6, the voltage drop is lower compared to table 5, while the receiving current is similar. Lastly, the reactive power in table 5 is 2 bar, but for table 6 is slightly lower, which is 3 bar. Lastly, for the conclusion is, based on the experiment, we are finally able to identify the characteristic parameter of lines compression under no load, during matching and during symmetry. We also know how to construct the circuit by considering the pollution. And finally, we also know the difference between the 150 km line and 300 km line. So that's all. Okay.
Okay, thank you.
So that's all. Thank you.